Okay, so in the previous three videos, we gave you some basic ideas about linear programming. Okay, and now we're going to use the next three videos to talk about linear programming formulation. That means, given a practical problem, how may we formulate that into a linear program? Okay, a key idea here is that according to the method that we're going to teach you next time, if you have any linear program, you can solve them in a very quickly way. Okay, so that means as long as you formulate a problem into a linear program, you have solved it. Okay, and that's why we really care about linear programming formulation. If you can do that, you can solve that problem, no matter how complicated the problem is. Okay, so that's something we must learn. We must learn how to formulate problems into linear programs. So here I'm going to give you two examples. The first one in the first video, the second one in the second video, and something else in the last video. So as we mentioned, we want to solve problems. We have that powerful solution tool to be discussed the next week. So we want to know how to formulate problems. The process is called linear programming formulation or linear programming modeling. And we will do more examples in the lectures, in the sessions, in homework, case assignment, exams, and the final projects. Okay, practice makes perfect. So we will give you a lot of chances to do this LP formulation practice. Okay, so after the two examples, I will talk about something called compact formulations. That will be something you must use when you want to formulate really complicated large-scale problems. So the very first example, eventually you will see that it's just a tiny example, is this product mix problem. Suppose we produce several products to sell, and each product requires some resources, and the resources are limited. So that means we cannot produce an infinitely many products. And now we want to maximize the total sales revenue with available resources. So we may imagine the following situation. We have different products to produce. Okay? And they require different resources. There are many products and there are many different resources, and the interaction or the interrelationship between products and resources are somewhat also complicated. And now we are asking, given all those things we have, how may we optimize the total sales revenue or optimize the product mix? So as an example, let's do something that is actually simple. We only produce desks and tables. Producing a desk requires 3 units of wood, 1 hour of labor, and 15 minutes of machine time. Producing a table requires 5 units of wood, 2 hours of labor, and 20 minutes of machine time. So that means there are 3 kinds of resources. Different products requires these 3 resources in different ways. Okay, and we have 2 products, 3 resources. Suppose that we can sell everything we produce, so that's not a big deal. All we want is to find the best way to mix our products. For each day, we have a limited supply of resources. So we have 200 workers, each of them works for 8 hours. We have 50 machines that each runs for 16 hours. And we have a supply of 3,600 units of wood. So we may see that here, we are really running a very big company. You have so many workers, you have so many machines, and you have such a large supply of wood. Okay? It is really because that we are dealing with a large company, so that we want to use operations research or mathematical programming, right? If the problem is small, all we need to do is to use our hands or use our pencil and paper. But because the problem is really large, so we really need to make good decisions. We really need to use operations research to help us to make better decisions. Okay, so anyway, supply, consumption. We want to decide how to produce and sell. The last piece of information we need is that desks and tables are sold at $700 and $900 per unit respectively. Okay, we have the prices. So according to what we mentioned about the DFSI principle, the first step is to define decision variables. We need to ask, what do we need to decide, or what do we want to know when we are going to make decisions or to conduct operations? The key information we need here is that we want to know what's the number of desks and what's the number of tables to produce in a day. So we define x1 and x2 as the number of desks and the number of tables produced in each day. Okay, these are the decision variables we have because these are the decisions we need to make. With these variables, the next step is to try to express the amount we may earn and the amount of resources we need to consume. If we can really do that, we can write down the objective function and all the constraints. So the second step is to do the formulation. First, let's work on the objective function. So we want to maximize the total sales revenue. Given the variables x1 and x2, we know the total sales is nothing but the 700 times x1 plus 900 times x2, right? For each desk, we can get $700. Together, we get 700 times x1. And we have two products. The amount of money I have is the sum of them. So I have my objective function as to maximize 700 times x1 plus 900 times x2. That's the total sales revenue, given my decision. And then I want to formulate constraints. For each restriction or limitation, we write a constraint. So because this is such a complicated situation, typically we summarize our data in this following way. We would like to organize all the related informations into a table or something that may help you get the ideas of the problem. We know that there are three different resources: wood, labor hour, and machine time. Also, there are different ways for desks and table to consume these woods. For each desk, we need 3 units of wood, 1 hour of labor, 15 minutes of machine time, and for table another way. And we also list the total supply. Okay, we have wood, we have labor hour, we have machine time. And then for the supply of wood, we know 3x1 plus 5x2 cannot be greater than 3,600. Why? This is the amount, the unit of wood we used to produce desks. This is the amount of wood we used to produce tables. The sum of them is the total amount of wood we use. This cannot be greater than the amount we have. Okay, so we have this supply constraint. For labor hour is the same thing, right? x1 plus 2x2 cannot be greater than 1,600. For machine time is the same thing, 50x1, 20x2. But here, this is the information in the information measured in hours. But the unit of measure here is minutes, so we translate that into minutes. When you are writing down formulations, keep in mind there is the unit of measurement issue. You need to make sure that all the numbers are obtained according to the same unit of measurements, so that you have no problem regarding interpreting those numbers. Okay, so our formulation can be found by collect the objective function, the constraints, by a representation according to the variables. We want to maximize our sales revenue subject to a wood constraint, labor constraint, and the machine constraint, machine time constraint. Okay, here I pose the question, is that all? Think about this. there are something that may be missing in this formulation. Think about that. Anyway, in any case, there are two things that you should do when you are formulating a linear program. You need to clearly define decision variables in front of your formulation. Okay? According to my personal experience, many people like to do this. For some reasons, they write down formulation first and then tell us what are their variables x1, x2 after the formulation. That's something that you should not do. Okay? You should first tell people what do you mean for your notations, because you create those notations. Okay? Before you make this explanation, no one can know what do you mean by x1 and x2. So when you define anything, that should be put in front of anything. Just like when you write, for example, when you write a C++ program, okay? When you write a computer program, if you want to use any variable, you need to declare them before you use them. Also, you are suggested to write comments after everything you have in your formulation, especially when that formulation is complicated. Okay? So again, this is very similar to what we are doing for writing computer programs, right? When something is complicated, we would like to write some comments so that we can remind ourselves or all those readers what we are doing. Writing comments definitely will help you to write correct programs and sometimes can help you write better programs. Okay? When you have a very complicated problems, you need to use comments to help us understand what you are writing and help yourself making sure that you do not miss anything. Okay, these two things you should keep in mind. So, the last two things we should do is to solve the problem and then do interpretation. Here, we still do not know how to solve that problem, but if you want, you may, for example, apply the graphical approach to the problem and then get an optimal solution like this. Okay? So now we have the solution, we want to do the interpretation, and then we make a difficulty. It seems to us that we should produce 884.21 desks, and again another fractional number for tables. Is that possible? It's impossible, right? We cannot produce a fractional number of desks and a fraction number of tables. So in some sense, our formulation is not so perfect. Our formulation may generate an optimal solution that cannot be executed. So we may want to ask, should we impose integer constraints? In some sense, we probably shouldn't allow our decision variables to be real numbers, right? We probably should ask them to be integers by imposing integer constraints. Okay? Probably that's one solution. Unfortunately, there are two things. First, if we put integer constraints on a linear program, that program becomes an integer program, and in general, an integer program may be too hard to be solved. Okay? If you have a linear program, the solver you have can solve that, can solve almost any linear program in a short time. Okay? But if you have an integer program, even if there are very few number of variables and constraints, it may take 1 day, 2 days, 1 week, 2 weeks for your computer to run without finding a solution. Integer programs are just hard, and we're going to tell you why they are hard later in this semester. But one thing we know for sure is that, if possible, do not add integer constraints, because that will make a very easy linear program to become very hard. But again, we know this suggestion is not impossible. It's not possible, right? But anyway, it still helps us in making decisions, right? We know these are fractional numbers, but never mind. Let's just suggest to produce, okay, for example, 884 desks and 189 tables. That's one suggestion, and certainly that's something we may do, right? Given the output of a mathematical program, or given the output of any operations research study, we get an output. Given the output, we make suggestions, right? And the manager, given the suggestion, the manager make decisions. In any case, in all this process, we do some adjustments, right? If we see a solution like this, we do adjustments to remove those fractional parts. That's something we can do. And this solution can still be much better than what we may get without using linear programming, right? So as long as linear programming can help us in this way, then it's good enough. So we know it may not really be optimal among all the integer solutions, but by ignoring the integer constraint, we only need to spend a very short time to solve a linear program, and we can still make a good enough suggestion. That's all we want. Okay? So, in this course, when you are asked to write a linear program, do not impose integer constraints. Okay? Suppose the question is asking you to decide the production quantity of a car. Okay? That doesn't mean you should ask the number of cars to be an integer. Okay? Sometimes you may need to do that, but typically do not. Okay? One reason is that we need to make the program to be solvable. Okay? Linear programs are much easier than integer programs. And also, typically when you need to make decisions, that must be because the scale of your problem is very large. If each day you only produce 1 car or 2 cars, that's not a big deal. You only need to use your pencils and papers. But when you remove those fractional numbers from something that are thousands or hundreds or millions, then those fractional numbers doesn't mean anything, right? So, in practice, we will not impose integer constraints on those products that should be integer. Okay? That's something for you to keep in mind. Okay, that's the first example.